Okay, so these were the last two. First, let's talk about this one. Anything to point out? Would you give this 100%? The two that did it said yes, they would give it 100%. Drew agrees. There is one thing that I would take off a small number of points for. One thing that I ask for in your mechanisms is that you show relevant lone pairs. Otherwise, we can assume all lone pairs in a structure. We are not required by bond line to show lone pairs. But if a lone pair is going through a change, meaning if it goes from a lone pair to become a bonding pair, I have to show that lone pair. It's relevant to the chemical reaction. It's relevant to the change. And there is a lone pair in this first mechanism on the right that I would say is missing. Do you see it? On the chlorine on the left. When chlorine attacks carbon, I want to see that lone pair. Without it, we're saying the arrow starts from chlorine. Chlorine is a nucleus when we represent it as just Cl. The electrons have to be explicitly shown. So that's a relevant lone pair. There are two other lone pairs on that chlorine and three lone pairs on the other chlorine that are not relevant because they're not going through a change. Fair? And then in the second step, chloride acts as a nucleophile. I don't need to show a lone pair there because the negative charge implies the lone pair. The negative charge is the result of an extra lone pair. And it is that negative charge that's driving this step. Perfect. A+. Remember in the formation of the halonium ring, in this case the chloronium ring, one chlorine attacks the alkene while the alkene attacks that chlorine back. The other chlorine breaks off. This is 100% correct. When I drew this, I actually would have shown this chlorine attacking and being attacked just because of proximity, but your arrows look very nice. It's wrapped very well. I want to point out earlier, is it okay if I erase this arrow? Earlier we had this shown. Chloride attacks the ring. A bond between carbon and chlorine in the ring breaks open. What's wrong with that? Good, you're tracking stereochemistry, right? This chlorine is wedged onto the structure, and I need to keep that bond on top wedged. So I can't break that bond. That's one useful way to look at it. There are more. Anything else that you guys see? Britton? Exactly. If chloride attacks here, this carbon already has an octet. It already has 4 things. For chloride to attack, something else is going to need to break. But as it's shown, chloride is bonding, and that carbon is keeping all of its electrons. But then on the top carbon, nothing is being added, but it is losing a bond. So one carbon would have 3 bonds, the other would have 5. So what I wanted to point out was whichever carbon in the ring chloride attacks, that's the same carbon that breaks its bond. Great. A+. By the way, what reagent do I need over the arrow for this reaction to be completed? Cl2. And what is the legal name for Cl2? Elemental chlorine. Great. All right. What reaction am I running on the right? it's not X2 because I don't add two X's. It's X2 with something, ROH. And the name that we'll call that is halo ether. Halogenation in alcohol gives us a halo ether product. So what reagents do I need here? Elemental chlorine, Cl2. HOMe. And what is home? It's an alcohol, specifically where R of ROH is a methyl group. So if you didn't want to put HOMe, you could put MEOH. That's actually the way that most chemists would put it if they're just putting it on a bottle. They'd say methyl alcohol rather than alcohol methyl. But there's absolutely nothing wrong with it. What's another way that you could communicate methanol? Instead of MEOH or HOMe, CH3OH, or even OHCH3. Perfectly legal, all of them. Which is why over the arrow I've put methanol with the methyl abbreviation, but then in the reaction, I wanted to show you that I can show it as methanol. They're exactly the same. There is not a difference. In English, when we write in letters, sometimes I'll put double T's next to each other and I'll just draw a line through them. But would you guys agree that that is exactly the same as writing my two T's with both their lines? They're definitely different, but they are communicating the same thing if you understand what they're communicating. That's what I'm trying to get across with this. I wouldn't care if you drew your two T's separate or if you crossed them together. And I wouldn't care if you did it one way in the first word and a different way in the second word, because I can understand what you're communicating. That's where I'm trying to get you guys to as well. I want you guys to be able to understand that communication. All right. Anything that we needed to add? Actually, who pointed out the chlorine-chlorine bond? Is that Annie? Calvin? Chlorine-chlorine bond needs to break. Which chlorine should it go to? To the one on the right. Good. Because again, just like last time, one chlorine is doing the attacking and being attacked. The other chlorine is going to leave as chloride. Anything else that you guys would change? Britton? And how do you rationalize that? Memorized it? Partial charge is always what helps us understand where to attack and where to attack from. Is there partial charge character on this alkene? Where is it, Jordan? What's the partial charge character? What charge is on the more substituted? Good. Because positive charges are more stable on more substituted, which means the less substituted is more negative. Perfect. So when the chlorine attacks, it makes sense that it attacks at the more substituted. When the chlorine gets attacked, it makes sense that it's the less substituted, which already has a stronger pull on the electrons, using the electrons to attack. I'll be honest, you give me this, I'll give you full points, because you've got the arrows correct. The pi bond attacks the chlorine attacks the pi bond. Full points for it. But it does help you understand the regiochemistry of the attack better if you recognize that the chlorine should attack at the bottom and be attacked from the carbon on top. This is best, but the other wouldn't have lost points. Active would have told you it's not correct. Active does care about the regiochemistry. So think about that partial charge. Jordan?
To
Lovely. Relevant lone pair, right?
Yes.
This is coming from a lone pair on the chlorine, and that's something that I do look for.
And then it makes sense why it attacks more substituted carbon, but the one that's going towards the chlorine, shouldn't it be coming more towards the bond? Because that makes it look like it's coming from the atom.
Sure, sure. You know what? This is such a challenging part with drawing and grading mechanisms, is I have to give the benefit of the doubt at some point, and that arrow starting from the middle, yeah, it does kind of look like it's coming from the assumed atom. But which of those lines is the pi bond? Right, neither one or either one. So if you started in the vicinity of the bonds in general, I did kind of assume that you recognized it was the pi bond attacking, which is different than without having the lone pair here, showing it start from the chlorine symbol. I don't know that you understand it's the lone pair. I want to see that relevant lone pair. But this one I would have given the benefit of the doubt to. I agree with you, Jordan, though, if it comes from the bond more explicitly, it communicates it even better. Does this look more appropriate?
Yeah.
Does it communicate it better?
Yeah. I personally think so. I guess I was just getting confused because it makes sense why we assign the partial charges for the chlorine going to those atoms.
Yeah.
And then the one going away from, I feel like it doesn't matter as much between the charges because it's all the bonds, like you said.
But it is this carbon that will use the pi electrons.
Okay.
This carbon is accepting new pi electrons. This carbon is accepting new electrons. It's going to have to lose something in order to accept them. That should feel similar to down here. This carbon is accepting new electrons. It's going to have to lose something. Yeah? Why is it that my chloronium ring here has no wedges and dashes, but my chloronium ring here had wedges or dashes? It would have been the same if it was dashed. Any idea?
Because you didn't put it on the product.
Yeah, and why isn't it on the product here, but it is on the product here? Inconsistency in your professor? Lack of foresight?
On a ring you have like
Axial versus equatorial. Now those don't show up quite as much on cyclopentane. They show up more relevant on cyclohexane. But I think actually we could say there are that is relevant, but not exactly why we showed it there and not here. Because it doesn't matter. Why does the wedges and dashes matter here? Cis versus trans. This proves to us that it's an anti-addition mechanism, which impacts the chirality. We got a chiral product. We did not get a meso product. Meso would have been syn addition, and this is not a syn addition mechanism. This is an anti-addition mechanism. So the chirality matters. This is also an anti-addition mechanism, but no, they're all tetrahedral, all sp3 hybridized. Good question.
It's because they don't have chiral centers.
No chiral centers. It's not a chiral product. It doesn't matter that it's anti-addition. It doesn't impact the stereochemistry of the product. If this were a syn addition mechanism, the chirality of the product would be meso. Because it's anti-addition, I get 2 chiral enantiomers. This is also anti, but there's no chiral centers. So the stereochemistry is not relevant. The stereochemistry exists, it just doesn't impact the product. But the regiochemistry does make a big difference. The methanol has to attack at the more substituted carbon. Why does it attack at the more substituted carbon? Why doesn't it attack at the other carbon in the ring?
It's more stable. And then I just assume since the chlorine hangs off.
Yeah, you know the next step is chlorine on the primary carbon, oxygen on the tertiary. But why does it attack tertiary? You said it's more stable. What is more stable? There actually is no carbocation. There's no carbon holding the positive charge. It's more substituted. So it's going to have a larger partial positive. Once again, we can kind of think of this as more negative, more positive, and the nucleophile, the partial negative of the oxygen, it's drawn to that more positive. In fact, this halonium ring is pretty equal. The two carbons are equally substituted. So it wouldn't have mattered which one got attacked. They both can get attacked. This halonium ring is not identical. In fact, if you look at the bond lengths, you'll actually see that the bond to the more substituted carbon is longer than the bond to the less substituted carbon. That's going to put more strain on the more substituted. And by strain, I mean its electrons are constantly closer to the chlorine. That's going to put a larger partial positive. That's going to attract methanol to it better. Yeah? Why is it a longer bond? Because it can stabilize that positive charge better. So if it has less and less and less electron density, because chlorine is pulling further and further from it, it's going to hold a partial positive, allowing for the methanol to attack. Anything I should add here? Lone pair on my oxygen. Oxygen's lone pair is causing a bond, not the oxygen atom, not the oxygen nucleus, the oxygen's lone pair. All right, and then I get this protonated ether. It's an ether now, but it has a proton on it. Anything that I need to change here?
The arrow should go to the hydrogen.
Yeah, it looks like it's pointing at the bond. But this should start from chlorine and show how chlorine takes hydrogen. One more thing. Perfect. Another arrow showing the OH bond breaking to oxygen. Kind of like up here, if the Cl-Cl bond wasn't shown breaking, there's no explanation for why it breaks. If the OH bond isn't shown breaking, there's no explanation for why it breaks. And if you practice your spot the difference, in each step lay out what bonds form, what bonds break, then make sure that you've got arrows that indicate all of those things. It helps you make sure that everything's there. Okay, how many times do you think it will take rehearsing these mechanisms to get them down? Anybody have it down already? You've got it? I didn't either my first time around. I spent many an hour at my local coffee shop in college practicing my mechanisms. And I'll be honest, I got them down. I knew the pattern. I did not understand anything. I didn't quite comprehend why the arrows were going the way they did, why the reagents were attacking the way they were, why I needed the arrows I did, why I needed the steps I did. That's what I'm trying to communicate to you guys, things that I wish I had known. The lone pairs are relevant in making these bonds, show them. The regiochemistry predicts the partial charge character. So rehearse that. Moral support. Practice, practice, practice. I would say, yeah, at least 5 times. And then one thing to actually do is copy a mechanism like you just have, and then do it from scratch. Do it from memory. and then go back and compare. Did you get all the steps? Were there any that you skipped? Did you get all the arrows? Were there any that you missed? The charges, the lone pairs. And then quickly, before I give you time to answer your question, I will grade these as the number of steps is proportional to the number of points. That's not a proportional arrow. So 3 steps could be 3 points. 3 steps could be 1.5 points. 3 steps could be 6 points. The number of steps will tell me how many points to assign the mechanism. And that way, I can split the points into your intermediates and your arrows. I'm considering, do you have your lone pairs? Do you have your charges? Do all of the bonds break when they should? Jordan and then Annie.
Yeah, on the actual paper for this one, it shows the chlorine pointing the other direction, and then the oxygen and methyl in the bottom middle, so that doesn't matter.
So the methoxy, right? Methoxy group. No, it doesn't matter. What you've identified is that the structure I gave you on the paper is just a conformational isomer. All of these bonds are achiral. All of these atoms are achiral. So they just have to rotate their groups around, just around this central bond mostly. Yeah, good question. Annie.
So you'll tell us how many steps you're expecting us to need.
Indirectly.
Okay.
Indirectly. You'll know how many steps that I'm expecting indirectly. I wouldn't necessarily look at it and say, oh, this is a 1-point problem. It's 1 step. It could be a 1-point problem, but it's 2 steps. And I'm just saying, I'll give half a point for all of the intermediates, half a point for the, or actually it'd be more like,
The starting material product and then like 1, 2, 3. Like you won't do that.
yeah. Okay, so for example, this is a 3-step mechanism. So I could give this 3 points. That means there would be a 1.5 for drawing your intermediates and a 1.5 for all of the arrows that you need to have. This is a 2-step mechanism. I could give this as 4 points. That means that you'd have 2 points for all of your intermediates, 2 points for all of your arrows. And I believe if you go back and look at the midterm, I did something similar where well, except that's not based on the number of steps. But in each step that you did on the midterm, I was looking at things like charges, lone pairs, bonds, and the number of arrows, and I was attributing points for those things I was expecting.
I just have a question on the one we don't, right? So if we had attacked the other carbon,
Yeah,
the wedge and dash would have been flipped.
correct. If you had attacked here, the product you would have gotten is this. How are those two related? They're not the same. They're stereoisomers. What type of stereoisomerism do they have? They're enantiomers. The 2 chiral centers flip configuration. So how do I control the chlorine attacking here and not here? I don't. I don't change that at all. This reaction leads to a racemic mixture, a 50-50 mixture of the 2 enantiomers. Good question. I gave you 1 stereoisomer, and I wanted to see that stereoisomer formed, but there is another stereoisomer that forms. All right, other questions on the mechanism before we move on? Great. All right, so back to the front page. We're looking at these reaction diagrams. What am I trying to think of? They're kind of like a roadmap, and they're going to help us relate all of our different starting materials. We've already started on the second one. We said that if I take this alkene and I react it with water in acid, I get 2-methyl-2-butanol. This was acid catalyzed hydration. Notice that I'm adding H and OH across the pi bond, thus the hydration. We said that this has a carbocation, which is important for why it got the rearrangement that it did. Calvin?
Can this be any acid? Is that just
It can be any acid. In fact, H3O plus doesn't really exist in the stock room. You generate H3O plus by dissolving a different acid into water. So you could do this with sulfuric acid, phosphoric acid, hydrochloric acid, nitric acid. All of those would help you in generating H3O plus. Good question. We said the regiochemistry for this is, maybe we didn't say this actually. This is a Markovnik. Did I even give you this? Oh, that's why. Okay. Sorry, I'm confusing you with my other OChem 1 students. I'm just kidding. I don't.
You started it at the beginning or at the very end. So you like gave us
The reagent.
acid catalyzed hydration and the different things on the arrow, and you said that it would require a carbocation, and we get the.
I see. So the regiochemistry is Markovnikov, which really only says hydrogen adds to the carbon with more hydrogen. But it tells us the carbocation forms on the more substituted carbon. Duh, that's the more stable carbocation, Markovnikov. And when it forms on the more substituted carbon, it's adjacent to a position where it can rearrange. So the carbocation rearranges before the water adds on. The stereochemistry is random. What that means is when hydrogen adds, if it forms a chiral center, it forms R or S, but the carbocation is not chiral yet. And when the oxygen adds on there, it can also form R or S, independent of what the hydrogen formed. So we get random addition. Let's look at this mechanism. In fact, we'll go back to the last page. No, sorry. The front of the last page, the second to last page, and we're on the bottom side. What I want you to keep in mind is that this mechanism is nearly identical to HX addition, but it always requires one more step. Much like how haloether is nearly identical to halogenation, but requires one more deprotonation step. All right, so we'll go on the left-hand side. You're welcome for making you draw something as clunky as an aromatic ring in this. What reagents do I need to add over the arrow? What? H2O and H3O plus. Great. Because I'm adding an H and OH, so I'm adding water, acid catalyzed hydration. If you're noticing that my double bonds inside of my aromatic ring are placed differently than the double bonds inside of this aromatic ring, don't worry about it. In fact, you can draw a circle inside of the aromatic ring in place of the double bonds. I just don't encourage it until you get into OChem 2 and understand better why the resonance is happening the way it is. But these are just resonance forms, so they're perfectly legal. Step 1, we have an acid-base step. Maybe a better way to call this would be protonation. What's my acid? H3O plus is my acid. So I'm going to draw out the bonds between H3O plus because I'm going to need to break one of them. Acid donates hydrogen. What's my base? Go ahead, Jordan. So is it this pi bond or this pi bond or this pi bond or this pi bond? This one? The alkene is my base. Because remember, we're in a category, we're in a section called what? Alkene addition reactions. What about this alkene or this alkene or this alkene? Those aren't alkenes. They're carbon-carbon pi bonds, absolutely, but they're not alkenes. They are part of an aromatic ring. And remember how we said functional groups have characteristic reactivity? Aromatic rings do not react like alkenes. So despite the fact that they have those pi bonds, it's not an alkene. All right, so the alkene is my base. My alkene attacks my hydrogen. I have some regiochemistry, so I've added my arrows, but do I understand how the two carbons are using their arrows? What is the partial charge across this alkene? What? Less positive, partial negative, partial positive. So which carbon is attacking? The partial negative carbon attacks. That's because it's partial negative. It gets to attack. That means we're following Markovnikov's rule. That means that the hydrogen adds to that carbon with more hydrogen. Guys, I want to apologize. I want to show H2O and H3O plus. So I'm having a second structure, H3O plus, H2O, conjugate base of H3O plus, H2O. Why did my carbocation form there? Why didn't the carbocation form on the other carbon? More substituted carbon, more stable carbocation. There is an added feature here. We're not going to talk about it too much until later. This carbon is conjugated with the aromatic ring. That means there's resonance that can happen with that carbocation. That's a powerful thing. All right. After after acid base, I have to consider carbocation rearrangements. Is there a more stable carbocation that can form? No. So no carbocation rearrangement occurs here. Step 2, nucleophilic attack. What's my nucleophile? H2O. Where does it attack? The carbocation. Great. Which H2O should I show attacking? Don't be silly. We're ignoring 100 billion of them. It doesn't matter which one I show attacking. So water attacks. Am I breaking either of the bonds between O and H? I am not. That means that I still have both bonds between O and H. Oh, that means H. So that oxygen takes on a positive charge. I want you to notice the conservation of charge. I started with net positive. My net positive stayed, but the positive charge moved. I have net positive. I keep net positive, but the positive charge is just being relocated. What's my last step? Acid base, we could call this step deprotonation. What is my acid? OH2? Like H2O? Should I take a hydrogen from water? Or should I take a hydrogen from this protonated alcohol? It's an alcohol with an extra proton. Or should I take a hydrogen from one of the carbons? Why not the carbon, Camilla? Yeah, those are not good acids. Carbon is less electronegative than oxygen. The more electronegative in the row, the more acidic. Okay, so I should either take a hydrogen from this oxygen or a hydrogen from this oxygen. When they're the same atom, how do I tell which one is more acidic? Remember karyo. Charge can help me predict acidity. More positive, more acidic. Which of these is more positive? The protonated alcohol. So water acts as a base and takes a hydrogen off of my newly formed alcohol. This does two things. First, it leaves me with my alcohol. Second, it regenerates my acid. And Calvin, what role did my acid play in this reaction? It's a catalyst, which means it should never be consumed or destroyed. It needs to be reproduced at the end of the mechanism. I started with H3O plus and water. I ended with H3O plus, catalytic. Yeah?
So, like in most reactions, I've seen catalysis on top of the arrow. So,
The arrow is no man's land. In fact, we don't have to use the arrow space at all. We could put everything to the side of the arrow. We could put both things on top. We could put both things on bottom. We could swap. Yeah, I'm not sure where all of the reactions are that you're seeing this, but in my experience, it is not standardized. Good question, though. All right, guys, that is the last mechanism that I'm going to ask you to know how to do. HX addition, acid catalyzed hydration, sister mechanisms. The only thing that's different is acid catalyzed hydration has this extra deprotonation step. Halogenation and the haloether halohydrin mechanism, brother reactions. The only difference is that halohydrin haloether has an extra deprotonation step. Practice those mechanisms. You'll see it on your unit test this weekend. Okay? All right, let's go through some more reactions. I want to continue hydrating my alkene. I want to add H and OH, but I do not want this structural rearrangement. So we will introduce oxymercuration, reduction. Sometimes just called oxymerc reduction. That is acetate, OAC. You guys remember that acetate is the 2-carbon carbonyl. So OAC translates into this. And you can draw that if you want to, but OAC is just a little bit easier to draw. This reagent on the bottom is sodium borohydride. What does that IDE at the end of borohydride tell us about the hydrogen? It's negatively charged. This is a source of H minus. That's what this is. Okay, sorry, the structure that it forms is 3-methyl-2-butanol. Does this have a carbocation intermediate? Does it place a positive charge on a carbon? See a lot of hesitant shaking heads. If it had a carbocation, I would expect it to form this structure, because the acid catalyzed hydration does have a carbocation. So no carbocation formed. it still has Markovnikov regiochemistry, and its stereochemistry is still random. So when chiral centers form, they do not form relative to each other. They're not syn or anti. I've now seen how to add water Markovnikov across an alkene with a carbocation and without a carbocation. But I have not yet seen how to add water anti-Markovnikov. This reaction is called hydroboration oxidation. This is borane, BH3. And for the same reason that borohydride is a source of H-, borane flips the partial charge that we're used to on hydrogen. Hydrogen is more electronegative than boron. So hydrogen takes the partial negative. And as we know, partial negative determines the regiochemistry. A partial negative will go to the more substituted. A partial positive will go to the less substituted. This is going to flip on its head Markovnikov's rule. So instead of H adding to the carbon with more H and OH, I'm sorry, this looks really confusing to me. This looks like I put a charge on my alcohol, and I don't want it to look like that. I want it to look like a carbocation, just in case that stood out weird. No positive charge there. I don't want to add H to make a CH3 and OH to make a secondary alcohol. Anti-Markovnikov will add H to make a CH2 and OH to make a primary alcohol. This is anti-Markovnikov. Well, first, let's be clear. No carbocation for this again. It's anti-Markovnikov regiochemistry. And its stereochemistry is actually syn addition. Now, it's a bit challenging to see that here, but we've got practice problems for us on the next page, and we'll look together at, really, I didn't put any practice problems that highlight the syn addition. Okay, so let's take a minute here to show a highlight of this. You guys are all good with this mechanism? I can erase it. Let's draw 1,2-dimethyl cyclohexene. Cyclohexene, 1,2-dimethyl. And let's react this with borane, followed by basic aqueous hydrogen peroxide. Hydrogen peroxide is my oxidizer of the oxidation step. By the way, these two reactions, they've got these numbers, and those numbers are significant. If I ever ask you to fill in a reagent that I've given to you with numbers, I expect you to fill it in with numbers. These are meant to be read as first, then. Not all together, but first react with this, then react with this. Those of you doing lab this week, synthesizing 1-bromobutane, you didn't really have to do a first, then. You mixed in butanol, sodium bromide, and acids. Mixed them all together. But then you added more sulfuric acid in an extract, then you added water, then you added sodium bicarbonate solution, those were sequential. And if you had mixed all of those together, they would have given you no effect because the acid mixed with the base would have canceled each other out. And it's something similar here. These need to be added separate or they ruin each other. Kirsten.
Specifically with the lab, if you had done them in a different, like those 3 steps, if you had done them in a different order, would that also have messed with the?
Maybe, because if you added the bicarbonate solution first, the solution is still quite acidic. So you would have gotten a lot of fizzing. You also want to add the acid first because if there is leftover alcohol starting material, it protonates it and pulls that leftover starting material into the aqueous phase, away from the product. So if you don't do the acid first, you don't really get rid of the alcohol right away, and that could cause problems. You want to get rid of it sooner than later, especially while it's still acidic, because the acid helps pull it out. Okay. Which carbon is more substituted? Neither. So it doesn't actually matter which carbon I add H to and which carbon I add OH to. The regiochemistry for this reaction doesn't apply. It can't be anti-Markovnikov because there's no difference in substitution. So I want to show syn addition.
Wait, you said this can't be anti-Markovnikov? I thought it was.
This reagent, or sorry, this starting material can't be described by Markovnikov or anti-Markovnikov because Markovnikov's rule depends on having a difference in substitution. A less substituted carbon, a more substituted carbon. Do you see how the H added down and the OH added down? The H and OH added syn to each other. Did I create any chiral carbons? Sure did. And I formed those 2 chiral carbons relevant to each other, respective to each other. Both of the methyls went up. The H and the OH are syn to each other. Is there any reason that I needed these chiralities and not the inversions of them? There's no way for me to even know, which means that this forms with its enantiomer. And we can describe that as racemic. Let's take this a step further. This is R1,3-dimethyl cyclohexene. And we'll run this through hydroboration oxidation. Basic, aqueous, hydrogen peroxide. Does the regiochemistry dictate anything about the product that we form here? Does the anti-Markovnikov's rule mean anything in this example? H will now add to the carbon with less H. Markovnikov's rule says add H to the carbon with more. So breaking Markovnikov says add it to the carbon with less. And if you don't like that, here's the justification for why it does what it does. Hydrogen is partial negative. Shoot, I flipped it around. Hydrogen is partial negative, and the more substituted carbon is partial positive. Those are going to align. Bromine is partial positive, and the less substituted carbon is partial negative. So those are going to align. So my hydrogen will be pulled towards the more positive carbon. So I keep the chirality of the methyl group that is not affected by the alkene. To the less substituted carbon, I'll add my OH. And to the more substituted carbon, I'll add my H, syn to my OH. Notice how I've added them both down because they're syn. I could also add them both up. Do you see how I'm describing the position of the H without telling you the position of the H? The hydrogen that was added is assumed now. You don't have to do that. Feel free to draw it in. The H is dashed. The H is wedged. The H and OH were added syn. It doesn't look like they were added syn because your eye is drawn to the methyl compared to the alcohol. But the methyl wasn't added, was it? The methyl is impacted by the hydrogen. What's the relationship here? Is this a racemic mixture? (50-50) enantiomers. All chiral centers flip between the two structures. Ah, then what is their relationship? Diastereomers. Some things change between them. Some things stay the same. What stayed the same? The methyl at the top, unaffected by the addition. So fun, right? So this is what we call a diastereomeric mixture. They do not form enantiomers because there was already a chiral carbon whose chirality does not change, while the new chiral centers do change. All right, one last one, and I will give you guys a break today. Sorry about that last class. It just got so late, and I wanted to finish the mechanisms. This is also relevant to alcohols. If we react osmate, that is OSO4. I just don't have a good way of drawing my S that doesn't make it look like a 5. Osmium tetroxide, OSO4, or if I run cold potassium permanganate. You guys are going to do this in lab next week, actually. Cold here actually just means room temperature, not boiling hot, which is relatively cold. I can take my alkene and I can add across it a diol. So the regiochemistry here is that I get a vicinal diol. The stereochemistry is that it is syn addition. So if I wanted to, I could actually highlight that those are added syn by drawing them both wedged. Think back to that mechanism we did earlier today. One of those carbons is achiral. So showing it with a wedge is irrelevant. It doesn't have chirality. But when we run it on a structure that does create chiral carbons, it is relevant. The chirality of the new carbons are respective of each other, syn addition. Cool. All right, let's take a 5-minute break, and let's be back here before 6:10 to round out the rest of our reactions. We've only got, wow, we're making good time. We've only got 4 more. Okay. And then we're going to practice them. Feel free to do this already if you want to. Fill in the ones that you recognize. Where you been? Yeah.
But I heard that.
You did. Good news? Really? You're in?
Yeah.
Congratulations.
Thanks. Yeah, it's like a big wait, but
Absolutely.
trying to figure out how to move and everything.
When is it? This summer? Yeah. Whew. So all the hard work paid off.
For your help.
I did nothing. You did everything.
No. It was helpful taking the midterm early.
Did it help bringing it to them? They like got something out of seeing it? Good. Good. Well, I'm excited.
Thank you.
That's a big step. Are you feeling any senioritis now with this class?
A little bit, but I still have to do well because
Yeah. Well, don't worry. I try my best so that you guys can do well. I'm really trying.
things for school, like they talk about functional groups and nomenclature.
Yeah. Yeah, absolutely. Good. More nomenclature coming up next week, too. Ew. Who's that?
Is it worth it to just work and you get your school paid for? Like it's stuff that we covered if you need it.
If you can get a job that will pay for school,
Yeah.
maybe.
What are you going for?
Engineering.
Will they pay for my school?
Yes.
Like, I'm in nursing.
Okay.
Please.
On the one that you just went over, what is that called?
It's called a vicinal diol, or it's called diol addition.
Oh, okay.
Yeah. No, thank you for saying that.
Is it hard to balance though?
In my new format, I have it's not well laid out with giving you guys space for notes and names.
So I would say this is different.
Yeah.
So if you do a full load,
Yes.
Because it's being added on. Things to think about.
A carbocation is when it adds where the alkene is not. So because this adds where the alkene is. Yep. Yep. In fact, if you're curious, there's some really cool stuff here. I'm not asking you guys to know these mechanisms, and so I kill time if I show all this stuff. Oxymercuration reduction is very cool because it gives you a mercuronium ring, which is a lot like the halogenation ring, the halonium ring. That's why oxymercuration doesn't go through a rearrangement. The hydroboration oxidation the alignment of the partial charges explains why the hydrogen ends up where it does. In fact, this is a concerted mechanism. Okay, oh man, this bugs me so much when a textbook does this. Textbooks will say, oh, the carbon-hydrogen bond has such a small difference in electronegativity, it's negligible, it doesn't matter. It's a difference of 0.4. And then they'll say, notice the difference in electronegativity between boron and hydrogen. It explains its regiochemistry. It's a difference of 0.1. And they're like, the carbon-hydrogen bond, who cares about its partial charge? Boron-hydrogen bond, that partial charge is significant. Pick a lane.
I don't know what I just walked into.
My soapbox. I'm showing you the intermediate of oxymercuration, and this is not the intermediate of hydroboration oxidation. I mean, it's close to it, but its explanation of the regiochemistry And then the explanation for osmate doing what it does is this. Oh yeah, those transition metal. Yeah, d orbitals. It is really lovely. It's like truly a beautiful thing. Anyways, notice how the osmium is actually getting reduced. It's getting electrons back from oxygen. Thus, the alkene is being oxidized because osmium is being reduced. So osmium is an oxidizing agent, or I should say osmium tetroxide is an oxidizing agent, so it gets reduced. Isn't general chemistry just flooding right back into you? And you can swap that out for manganese, which is why osmium tetroxide or potassium permanganate do the same thing, because you can just swap out that transition metal. It's very fun. Okay, I want to show you guys a tool that I have not yet heard from any students has been useful. But I love it, and I share it every semester because I can't imagine how it can't be useful. So class resources, no. External resources, because it's not built into the class. I highly recommend ChemTube 3D as a way of visualizing these chemical reactions. If you were to ask me, how do you grasp all of the reactions that we do? This is how I think of them, but I think of them in three-dimensional space, running into each other over time. So we are doing electrophilic addition to alkenes, which means that the alkene is predominantly acting as the nucleophile here, like nucleophile, nucleophile, and we saw it act as a nucleophile with these acid-base reactions. Let's look at this regioselective addition. Doesn't this look a little familiar? Does it? What do you see, Calvin? Yeah. It should look a lot like the mechanism we did at the start of class, except with elemental bromine instead of elemental chlorine. All right, so here is the alkene. Geometry, flat. Notice how it's flat? I'll see if I can zoom in on this better. And also, I would, yeah, I hate it when it does that. I kind of want to see if I can get this on the camera too. Alkene is flat. That means that this reaction can happen from its top or from its bottom. If it looks like it's happening from the top, just flip it over. Now it looks like it's happening from its bottom. So really almost any time you think it's happening from its top or bottom, well, I guess it depends on whether it's symmetric or not. Sometimes you can flip it. All right, we can actually play this out. On the bottom, just kidding. Controls. And then on the bottom, it will give me the ability to play this step. I swear, I promise. Okay. I'm not sure what it's, nailed it. All right, here it's playing, and you can see how the bromine added to both carbons and then broke off from the bromide. Then we have this bromonium ring. Notice the bond lengths. It's longer to the more substituted carbon because that carbon can put up with having less electron density around it. That's just building a really strong partial positive on that more substituted carbon, which is why the nucleophile adds there. Here's that step. Carbon-oxygen bond forms. Carbon-bromine bond breaks. Notice how the oxygen took on the positive charge. Now, I'm showing deprotonation. Unfortunately, it's not showing a conjugate base coming in. It's just saying H plus drifts away, which would literally be just a proton floating away, which could happen, but maybe is not the most likely. This right here is showing you a transition state. What is a transition state? Where bonds are actively breaking and forming. For instance, is this breaking open the halonium ring, or is it forming the halonium ring? No. I mean, yes. And no. It's actively forming and breaking. I don't know. If this molecule got to this stage, and then another molecule, boop, just ran in there onto that bromine and shoved that bromine back down, it's going to keep the halonium ring, and it's going to electrostatically push away that molecule of methanol. The halonium ring is not being broken open. I don't know that. It could be forming. Or if a molecule comes down here, pops my methanol further up, that is going to break open the ring. This is not breaking or forming the ring. It is both. It is the transition state between the ring being open and the ring being formed. But it itself cannot tell you what direction things are going. And why does it use those dotted lines? To indicate that those bonds are not formed or broken. They're in the process of changing. In what direction? That's when I do this. In what direction are those bonds forming? Not for us to say. Is that fair? Okay. The last of our reactions. These are maybe some of the misfits that don't really go with the others. You'll notice that the top ones all have halogens. The middle ones all have alcohols. These bottom ones are a bit all over the place. What else has changed in this process? Sorry, for this diagram, what else has changed? Say that one more time. Some of them give us two products. That's true. The alkene is different. This is a structural isomer of the alkene. It's not the same alkene. And I did that because I wanted different regiochemistry on the alkene for the reactions that form two products. I didn't want to use the one that was on the a terminal alkene, the mono substituted. Okay, let's start by going up to the left. What functional group do I start with, and what functional group do I form? Alkene to alkane. This is referred to as reductive hydrogenation. But reductive hydrogenation, in my opinion, is redundant. Because if you're hydrogenating, adding hydrogen, you are reducing the carbon. So a lot of times it's called reductive hydrogenation. It requires hydrogen gas and a catalyst. And that catalyst is palladium mixed with charcoal. So we call this palladium on carbon. You guys will do this in lab in a few weeks. We don't say this explicitly over the arrow, but it is always assumed that hydrogen is in excess. And that's because the hydrogen is a gas, and controlling its stoichiometric quantity is always very challenging. So when you run this reaction, you always assume an excess of H2. If we go down to the left, what functional group do I form? Bit of an obscure one, but if you don't recognize it now, get to know it. This is the epoxide. This is epoxidation. And to run epoxidation, I need a peroxy acid. We can abbreviate peroxy acid as some carbon chain attached to CO3H. And the most common, the one that you'll see from me, is MCPBA. M stands for meta, which is the structural placement of the chlorine to the peroxy acid on the aromatic ring. They are said to be meta to each other. Metachloro peroxy benzoic acid. What does peroxy mean? Yeah, oxygen-oxygen bond. Kind of like hydrogen peroxide. Here we used hydrogen peroxide, and hydrogen peroxide has this OO single bond. So a peroxy acid is the combination of a peroxide with a carboxylic acid. It's not a carboxylic acid. It's not a typical peroxide. It's a peroxy acid. This has such a cool mechanism. In fact, we can see it. Oh, I just realized the camera is facing the wrong way for the board. We can see it on here, electrophilic addition to alkenes, epoxidation with peroxide. You see the epoxy acid, carbonyl OOH. Watch this. I wish it would do that slower. That was so fun, wasn't it? Oh, I can do it slower. Do you see how that oxygen that becomes the peroxide came from the peroxy acid group? And then the original oxygen of the peroxy acid, the acid part, actually transitions into becoming a carbonyl at the end. So the peroxy acid basically has an excess oxygen, and it gives up the oxygen and gives us a byproduct, carboxylic acid. And it goes through this super fun transition state. Isn't that incredible? 5-membered ring on one side fused with a 3-membered ring on the other. We don't have to say this. But we do up above, sorry. This reaction is syn addition. We don't have to say that because if 2 carbons are connected to the same thing, they have to be on the same face. So this is syn addition. But I did miss with hydrogenation. This is also syn addition. And that's important because each carbon bonds to one hydrogen. So if they both create chiral centers, those chiral centers will form respective to each other syn. All right, let's go to the top right. This is where we will form 2 products. This one I think probably looks the least like any of the other alkene addition reactions, yeah? Because I'm not just adding 2 things across my alkene, I am cleaving the alkenes. So this is called oxidative cleavage. Both of these are considered oxidative cleavage. What functional groups do I form on the top? Name one of them. What's the structure? What's the functional group on the left? Ketone. What's the functional group on the right? Carboxylic acid. You know your functional groups. That's the regiochemistry here. The regiochemistry is what functional groups will form. If my carbon of the alkene has carbon chains, I'll form a ketone. If the carbon has a hydrogen, the hydrogen gets oxidized. That is replaced by an OH, and it gives a carboxylic acid. There are two reagents that can run this reaction. One is oxidative ozonolysis. So that is O3 with H2O2. H2O2 is acting as an oxidizing agent. It also acted as an oxidizing agent in hydroboration oxidation. It also essentially acted as an oxidizing agent in epoxidation. Or you can run this with hot potassium permanganate. Quite the difference from running it cold, isn't it? Cold does add 2 oxygens across the alkene, but cold doesn't have the energy to cleave the carbon-carbon bond. And I do want to point that out. You can predict the products of oxidative cleavage by simply redrawing your alkene, exaggerating that carbon-carbon double bond, erasing it, and replacing the alkenes with carbonyls. Then oxidize any hydrogens. The reaction just below it does essentially the same thing, but it actually keeps that carbon less oxidized. It doesn't swap out the hydrogen for an oxygen. So what functional group does that form? Ketone and aldehyde. If it's less oxidized, that means it's more reduced. So we call this reductive ozonolysis. We run O3 and we use either DMS or zinc. Oxidative ozonolysis. Reductive ozonolysis. The DMS is dimethyl sulfide. That just starts as 2 methyl groups on sulfur, and it forms DMSO. You can see how it physically, chemically, absorbs an oxygen from the reaction. So it acts as a reducing agent because it gets oxidized in the process. Zinc does essentially the same thing. Zinc just forms zinc oxide salt. It chemically absorbs an oxygen, helping to keep the product more reduced. All right. We have 20 minutes. What I would like for you guys to do is look at these structures. Keep in mind the numbers on the side tell you how many structural and stereoisomers are capable of forming. And then on the bottom is a bit of like a reaction roadmap. So there's one reagent here that can be used to form all of these different structures. We need to deduce the reagent. we can see that there is a cleavage reaction. That can actually help me stitch together what my alkene. We can see that there's an alkane product formed. We can figure out what reagents would be necessary there. Once we figure out what the alkene looks like, then we're going to show the product that it forms with two other structures, with two other reactions. So split your time between these. What you need to do is be able to reference your reagents and identify what change they're going to give you. Does it give you a more substituted alcohol, a less substituted alcohol? Does it give you a diol? Does it give you an epoxide? Does it give you a vicinal dihalide? Does it give you a vicinal halohydrin? Does it give you a vicinal haloether? You need to be able to relate the reagents to the products. Get familiar. I'll come around and answer questions as you fill them in. And yeah, please feel free to work together. If you feel like this makes sense to you, then be selfish and help the people around you, because by answering their questions, you're going to start realizing more and more what's going on. No, I was lying.
You do?
I have 3 extra.
Okay.
I just lie a lot. Sorry. Teasing. Sorry, I should have given it to you earlier. Well, you were today, right? You want to really practice this stuff? Do the practice final. Do my practice old homeworks. Get really familiar with these things.
So what do you want us to do?
Predict the product, or actually the products that form. And then for this one, predict the starting material that gets you to these. That's right. Nice. Okay, so I actually didn't clarify this up here. But notice how this has 2 hydrogens. Both of them will get oxidized in oxidative conditions to give 2 carboxylic acids on either side of the carbon. And this is a hydrogen connected to the carbon.
So this would be an OH?
Yep.
Okay.
And this would be an OH.
It gets 2?
It does. All of the hydrogens will get oxidized.
Okay.
Mm-hmm. And do you know this chemical?
No.
It's in your blood, and it's in your sodas, and it's in a lot of carbonated things. It's
No idea.
carbonic acid.
Carbonic acid.
And carbonic acid is known for decomposing. It breaks down into carbon dioxide and water. So if you ran this reaction, you would actually expect to see some bubbling from the carbon dioxide that comes out of it. I'll put that one on the board before we leave.
So with that one, you would never like cleave it, because as an oxygen you just cleave it from like the carbon-carbon alkene, right?
Is this an alkene?
No.
Right, there you go.
Okay. Yeah.
Yep. So far, since we're only focusing on the alkenes, all of the other functional groups will be assumed to be inert.
Okay, so you wouldn't even like.
Yeah, you're right. Not an alcohol. A carboxylic acid.
Oh, right.
This? would be the product from that alkene. Is that the alkene we have? No. So my recommendation is redraw that whole structure, exaggerate the carbon-carbon bond, and then cleave it. And then remember the regiochemistry. If there was a hydrogen attached, then the hydrogen gets oxidized to OH. If there's a hydrogen attached, it gets oxidized to OH. If there's a hydrogen attached. Mm-hmm. Mm-hmm. Yeah, but remember that's not actually changing the hydrogen.
Oh, you're right.
You still have your hydrogen.
What? Oh, what is going on? I'm so confused.
Well, okay. Don't get rid of the carbonyl.
Hold on. See, this is where
Let me put it in this context to you. If the alkene carbon has a hydrogen, it becomes a carboxylic acid. Well, no, because the bond gets cleaved and becomes a carbonyl, and the hydrogen gets oxidized to OH. This is a carboxylic acid. So when doing the cleavage, form the carbonyl where the alkene bond used to be. And then look at if there are hydrogens attached, oxidize the carbon to a carboxylic acid. Yeah? Whoa, you were really fast. I'll be right back. This carbon has disappeared.
Okay.
Carbonyl 1, 2.
Oh.
Carbonyl
then-
1, 2.
And then, but I have the right idea. I just can't count.
But
No.
no carbonyl. So 1, 2, here's my alkene.
That's where a carbonyl should be.
That's where the carbonyl should be. Perfect.
And then
And this gained a carbon from somewhere. One
right
carbon,
there.
one carbon. 2 hydrogens,
So it should be.
2 OHs.
Oh, so each. Okay. Okay, that makes.
There you go.
Okay, that makes sense.
I'm getting thrown off by this ketone here.
The ketone's not going to do anything,
That's why, like,
but this carbon of the alkene looks a lot like that carbon on the right of the alkene, right? This carbon is bonded to one carbon group and has one hydrogen, and that carbon was bonded to one carbon group and then became a carboxylic acid. So this carbon here becomes a carboxylic acid.
and that's just the
Good. Well, that would imply that there were 2 other carbons here. But actually, a hydrogen will get oxidized to a carboxylic acid, and a hydrogen. Mm-hmm.
okay.
There you go. So both sides.
On both sides.
There you go. Both of the hydrogens get oxidized.
And then
So this is the right idea, but your carbon chain doesn't look the same. Your carbon chain looks like that. That's just an example alkene. All I need you to do is apply it now to the new carbon chain.
so this is like that. This comes off, and that is right there, and then
Yeah, if you were mapping your carbons, I would say 1, 2, 3, phenyl. 1, 2, 3, phenyl. The alkene is 1 and 2, but your epoxide is not 1 and 2.
so let's just draw this part here,
Mm-hmm.
and then you got 1, 2, so 1, 2, and then 3, 4.
Good.
What's that? That's the 3.
Here's 3, 4,
Yeah.
3, 4,
Oh, 3, 4.
and the alkene between 3 and 4, so the epoxide between 3 and 4. There you go.
Okay.
Yep. Elemental chlorine. Actually, yeah, this one's right. Great job.
Okay. I was thinking like really thrown off by the ketone on there, but like on that one, it's just Cl2,
Yep.
and then
And you've actually added H and Cl. You went from CH2 to CH3.
is there another Cl here?
But our reaction with adding X2, Cl2, is that the two carbons of the alkene become a vicinal dihalide. So there won't be any rearrangement like you've suggested. Good.
And that one just reduces it to.
Sure, but notice that there's two structures. So I want to see the stereoisomers that form. And that reaction has what stereochemistry? Syn addition. Here, this is perfect. This one you lost a carbon. Carbonyl 1, 2, 3, carbonyl 1, 2.
And then there's another. Oh. So
Yes.
One,
Yep.
Yeah, let me just redraw it.
Good idea.
So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then OH? No, and then another one OH. So
Yes.
1, 2, 3, 4, 5. Okay.
Perfect. Good.
And then that one.
This one's right. You're just missing that bond between it and the O. Good. And then this, you've got one of the two structural isomers, but you haven't showed any of the stereochemistry, and that's why there's 4 products. There are 4 total combination of stereo and structural isomers.
I have a question on this one. So I cleaved it down here.
Yeah.
Carbons.
Nice. You nailed it. That one looks perfect.
Is that like that?
Absolutely.
Okay.
Great work. Yep. 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 Great work here and here. Oh, actually, it's not going to rearrange.
Why?
Secondary carbocation is where it forms. No greater stability on a secondary carbocation adjacent.
It's way out here.
Yeah.
I thought there wasn't a carbocation on this one though.
There is a carbocation. But that doesn't mean the carbocation rearranges. Notice our mechanism on carbocation rearrangement.
So for something like this, are we expected to go through each of those steps to?
No, but those steps can help you process it. So what I would say is, on the reactions where we know there's a carbocation, consider the regiochemistry. Where will the carbocation form? You predicted that it would form on the secondary carbon, not the primary, because it's more stable on the secondary carbon. But then you assumed that it would rearrange. But the question is, does it have an energetic preference to rearrange? On a secondary carbon, it's not going to rearrange to a primary, and it's not going to rearrange to a secondary.
So if this one,
Yeah.
we know this one has a carbocation because it rearranges.
Correct. But not everything with a carbocation
Has to rearrange.
has to rearrange. Here, the carbocation formed on that tertiary carbon,
Oh yeah.
no rearrangement necessary, no rearrangement feasible. And this one, by the way, we didn't show it, but this one has a methyl shift. This has a rearrangement.
So if it has a carbocation, it could rearrange.
It can rearrange.
If it doesn't have a carbocation, it's never going to rearrange.
Exactly. Exactly.
It will only rearrange if it's more stable.
And adjacent. Directly adjacent.
Yes, but this one is adjacent, but it's not.
Not more preferable. Good. You lost a carbon. You lost it here too.
I did where?
1, 2, 3, 4, 5. 1, 2, 3, 4. What would be a way around that? How do you make sure you don't lose carbons when you draw a product? How do you make sure that you keep the right number of carbons? Count your carbons, map them, use some sort of numbering system or lettering system or symbols to keep track of where your carbons are in the structure, starting material, and where they are in the product. Lost a carbon. Right? Oh no, you didn't. Sorry.
Yeah.
You didn't.
How terribly wrong. How far off are we on all of these?
You did not form a carboxylic acid here.
So we're supposed to form a carboxylic acid here?
Yeah,
but not
where
there or in both places?
actually on anywhere there's a hydrogen in oxidative ozonolysis. Take care, Christine. Anywhere there's a hydrogen will get oxidized. Hydrogen gets oxidized. Two hydrogens both get oxidized.
So that means that they're going to gain electrons.
Oxidation
Oxidation
is loss.
loss. Okay, they're gaining electrons.
And what you can see on the board is when we did oxidative ozonolysis, top right, only one of the carbons had a hydrogen, and that hydrogen became an OH.
Okay, so
Here, one of the carbons has one hydrogen, so that will become an OH. One of the carbons has two hydrogens.
this will
The
just,
carbonyl is correct, because the carbonyl has to form up there too.
so this is gonna be here, but this is just an OH.
Yeah, so when I say the hydrogen turns into OH, what I mean is, in addition to the carbonyl you get an OH, meaning you form a carboxylic acid
Okay, and then this will also be a carboxylic acid because.
at both positions,
Okay. Okay.
at both hydrogens.
Okay, I understand now.
But then show me, at both positions. You actually have added a carbon to your structure.
Technically, I haven't.
1, 2, 3, 4, 5, 6.
Oh.
1, 2, 3, 4,
you're
5.
Right, I have. Okay, so then.
It's okay.
What happens here?
Both of the hydrogens get oxidized to carboxylic acids.
But how do I draw that?
Don't have a hydrogen there, make it a carboxylic acid.
Instead of.
A hydrogen,
I know.
have an OH. You have a hydrogen there right now, because you just erased your extra carbon.
Oh, so it's OH on both sides?
Yes. Every hydrogen will get oxidized. That's right.
I understand now. That was rough.
So on that first problem that you guys were working on, so we said that we can exaggerate this carbon-carbon bond, and that is helpful because then I can just erase it, and I can predict my carbonyls. And since I had oxidative conditions, anywhere that I have a hydrogen gets oxidized to a carboxylic acid. So here was a hydrogen oxidized to a carboxylic acid. Here was a hydrogen oxidized to a carboxylic acid. Here was a hydrogen oxidized to a carboxylic acid. And this product is carbonic acid, which will actually decompose and leave the reaction as carbon dioxide. The same reason your soda fizzes. When you mix it, you're decomposing some of that carbon dioxide, decomposing that carbonic acid. Okay, yeah. Yeah.
This one, I know it has to go on no substitute. Would that be the case then? Or would it go on one of these? Right?
So the carbocation wants to go on the most substituted. Which carbon of the alkene?
They're equally as substituted.
Good, which means it can go on both.
Okay, so that means.
But it won't go on this one because that's not a part of the alkene.
Okay, perfect. I just want to make sure.
How do you know what that one is? It's not in our notes.
HCl,
Yeah,
HX.
it's H halogen. Mother trucker.
Sorry, not clear.
That's okay.
Now, how many products are going to form?
2.
No,
4. Sorry.
sorry. 4 products will form. That's because the hydrogen could add wedged while this adds
could do
dashed,
Okay.
or they can both add dashed. Actually, 4 might have been cutting it short. But the carbocation could have formed here, and then the chlorine would add there. The carbocation could have formed here.
And then it would be could be wedge or dash in each position.
Yeah.
Me too. That would be 4.
Actually, but it's the combination of the chlorine.
Oh, so it would be 8.
The chlorine and the hydrogen could both be wedged or dashed. I think it's 8.
I think it's 8.
Yeah. And the same thing here. Yeah, so this one's got like 2 products. That's because you form a chiral center, so you can get the wedge and the dash at that chiral center.
So I could do this, or like, you know.
Yep, exactly.
Wait, okay, thank you. Real quick, do these have names? I only got halogenation for these. No.
Halogenation is its name. This one is often just called HX addition,
Alright,
or it can be called hydrohalogenation.
alright,
This is halo ether,
yes.
and this is halohydrin.
Okay, cool. Thank you.
Yeah.
When you want a regiochemistry, it's like inside, outside.
Do you mean stereochemistry?
Yeah, stereochemistry.
Yeah, because regio is right. You added it to the more substituted carbon. The stereochemistry is it can add wedged, it can add dashed.
And that one is like,
Yes, exactly.
okay.
Anti-opposite, anti with different regiochemistry. Exactly.
And then that's like when we reduced it.
Perfect.
Okay.
Exactly right.
Do I need to put like,
You can, but this should, I think, form 8 products, not 4.
because it can be.
Take care, guys.
Wedged or dash on this one, and then wedged or dash on this one.
And this also becomes wedged or dashed.
Oh,
So they can be both dashed, both wedged, wedged, dashed, wedged, dashed. That's 4.
the methyl group itself.
And then they flip, and they become wedge, dash, dash, wedge, wedge, dash, dash, wedge.
Okay.
So 8 total products. The methyl group becomes wedged because the hydrogen that's adding there is dashed or wedged.
Okay.
So you see it in the methyl.
That's a lot.
Uh-huh. Fun stuff, right?
Yeah.
Unit test this weekend.
Oh gosh. Oh, because you can take your tests at home, right?
Yeah, over how many days? Like 4 days?
That's nice.
Are you teaching
Yeah.
in the summer?
I am. 8 a.m. OChem 2,
Oh, that's what I have.
3 days a week. Good, that's me then.
The one I can fit in because of my work, but
Good,
yeah.
I'm excited. I love my 8 a.m. OChem 2. For whatever reason.
We had to convince you to teach
Take care, guys. Good luck on your unit test this weekend. Did I mention that enough? I hope so.
What are you doing right now?
I am just wrapping up OChem 1.